Today we're going to talk about line integrals. So how is this connected to what we've done before? Previously, we had a function y equals f of x, and we could integrate it over an interval of x values, say from a to b. So here's what we're going to do now. We're going to do a couple things. First of all, we're going to take a scalar function f over a parametric curve c, and then we're going to integrate that over an interval determined by t values, since that's the parameter. And this is called the scalar line integral. What we're also going to do is we're going to take a vector function f, and we're going to integrate that over a parametric curve c, and that's going to be called a vector line integral. And then we're going to see what the connections are between these two things. So first, scalar line integrals. Let's look at what it means to integrate a function over an interval. So previously, we had integrating y equals f of x over an interval of x values. So what could it mean for us to do the thing that we're doing now? So here we go. So on the left, we've got the graph of the thing that we've seen before, the thing that you should be familiar with. So what are we doing now? Instead of going straight from A to B along the x-axis, we are moving along a curve C, and in this image, the curve C exists in the xy plane. And again, it's a parametric curve, so it can go anywhere. So x is a function of t and y is a function of t. But you could still think of there being function values, which you can imagine as heights in the z direction. And we could still imagine this area along the curve, and it's being simulated by rectangles. And of course, our input parameter is t, so that's the variable that we can use to express the entire expression. Okay, so let's summarize all the changes and updates in this table. So first off, comparing the classic case y equals f of x to the parametrized case, which you could think of in any of these forms that we've seen before. So just function f is really a function of t, but we think of it as a function of x of t and y of t. But of course, x, y is really just position function vector r. So in the classic case, the variable is x. Parametrized case, the variable fundamentally is t. So what about the rectangle height? In both cases, it's just going to be the function value. Now, what is the width? Here's the fun part. So in the old case, and again, we're starting with the approximation. In the old case, it was a change in x value, delta x. What is it in the new case? It is a piece of length. Now, how do you find the piece of length? The way that we do it is we use the Pythagorean formula. So little change in x squared plus change in y squared, square root of all that, gives us the length of some little piece on this curve that's moving all about the xy plane. So now that we know the height and the width, we can say what the area is for one rectangle, and then we sum them all up. So in the old case, in the classic case, it was the sum of f times delta x. In the new parameterized case, it's the sum of f times delta s, because that's the new length. And of course, that's the approximation. Now we have to say what it is exactly. Exactly, in the classic case, the integral is x goes from a to b of f of x dx. Now what about in the new case? Well, it was the sum of f times ds. So now just turn that into an integral. It's going to be the integral of f, where for a moment we'll just write it in the original expression, f of xy ds, and we're integrating over the curve c. Now, what does that mean in a way that we can calculate it? We need to re-express everything in terms of t. So we'll be given for our curve the starting and ending values of t. So we're going to integrate from t goes from a to b. Next, what about the function? The function is a function of x and y, but x and y are themselves functions of t. That will all be expressed in terms of t. And then finally, ds, we've encountered this before. This is just the formula for length. So it's the square root of dx dt squared plus dy dt squared, all of that dt. So we've now written everything expressed everything in terms of t. We now have an integral in terms of t that can now be calculated. So I like to think of starting with this sort of generic formula, but then turning it into an expression in terms of t and one that we can calculate. So let's do an example to see how this works. So here's a function, find the area under f equals x cubed y to the negative 1 over the curve C, which is defined in the following way. Y equals x squared as x goes from 2 to 3. Okay. So step 1. We want to rewrite everything in terms of a parameter, which is t. So an easy way to do this is to say, just let x equal t, and then y is t squared. Okay. And since x goes from 2 to 3 and x is t, t goes from 2 to 3. Next, we know when we set up our integral, we're gonna need dx dt and dy dt. So dx dt is 1, and dy dt is 2t. And let's also parameterize the function. So the function is just t raised to the third power, and then t squared raised to the negative 1. And that just simplifies to t. So now we can just set up our integral. So the basic formula is the integral over the curve of your function ds, but now let's translate that into, rewrite it using t, and we'll have something that we can do. So it's the integral as t goes from 2 to 3. The function is now t, and ds is the square root of 1 squared, which is 1, and then 2t squared, which is 4t squared, and then all of that dt. And now we have to do, so this is the integral, we finally set it up, and now we're just back in single variable calculus, we just have to calculate the integral. So to do this, this is just a simple substitution. U equals 1 plus 4t squared, du equals 8t dt, and then the integral can work itself out. Now, of course, the key part I want to focus on is doing the setup, because that's the new thing. So I hope this part makes sense. The rest is just basic single variable calculus. So let's check it out. So the integral of, we get u to the 1/2 and then times 1/8 du. I'll just put the 1/8 in front. The integral of that is going to be u to the 3/2, and then divided by 3/2, you straighten out the constant, you just get 1/12. So now, let's see, here I chose to put it back in terms of t. So putting it back in terms of t, and then evaluating as t goes from 2 to 3, plugging in t equals 2, t equals 3, you get 1/12, 37 to the 3/2 minus 1/12, 17 to the 3/2. And that does not simplify, but it works out to about 12.9. Okay, so that is your basic case of how do you do a line integral over a curve. Now, in this particular case, it seemed we didn't really need to use the parameter t, because our curve is defined with y as a function of x. We really could have just done everything in terms of x. Okay, but this was practice because we know that typically parametric curves are written parametrically for a reason. Y is not a function of x. So let's take a look at that example. Let's find the area under this function, f equals 3x minus 4y, over C defined by the left half of a circle centered at the origin with a radius 1. So we have to go through all the same steps, but now it's we definitely have to do it. So it's a circle, radius 1 centered at the origin. We know the parametric formula for that curve. So the first thing we have to do is parameterize, and the formula for that curve, x equals cos t, y equals sine t. Now, it is the left half of the circle. So for the left half of the circle, we know the angle is going from pi over 2 to 3 pi over 2. So those are the bounds for t, since we're using t like our angle. That's the first. We've parameterized our curve. Next, parameterize the function. So now we know that f is just 3 times cos t minus 4 times sine t. Okay. And now we go to our line integral, our scalar line integral formula. So the scalar line integral is just the integral over the curve of f ds. So what does that mean? We have to write in terms of t 3 things. For the curve, what are the boundaries? T goes from pi over 2 to 3 pi over 2. First thing. Second thing, your function, that's 3 cos t minus 4 sine t. And then finally ds. So we just need to take the derivatives. So dx dt is negative sine t, and square that. Dy dt is cos t, plus square that, and then square root of all that business, dt. And now you have an integral that you can go ahead and do. So that's the setup, and now let's do the integral. So of course, square root of sine squared t plus cos squared t, all of that is just 1. So this just simplifies to integral of 3 cos t minus 4 sine t dt. So you just get 3 sine t plus 4 cos t evaluated from t goes from pi over 2 to 3 pi over 2. You just plug it in, and you get negative 6. So a couple of comments about this calculation. So I actually said the left half of the circle. I didn't technically say where to start and where to stop. So we just chose naturally because we chose naturally to go from t equals pi over 2 to 3 equals pi over 2, just because that's the natural thing that we do. Smaller value, larger value. Technically, I could have said start at the bottom of the circle and go to the top of the circle. And that would reverse the boundaries of integration, which, as we know, would actually change the sign of the result. Okay. So actually specifying which way you're going is actually important. So choosing a direction for a curve is called an orientation. So of course, changing the orientation of the curve changes the sign of the result, but not its magnitude. So for single variable calculus, when we have a path or an interval, changing the orientation is just the same as switching the boundaries of integration. So there's another important thing, which is we chose, we said it's a circle of radius 1 centimeter at the origin, so we just always use y equals cos t, x equals cos t, y equals sine t. However, as we've previously learned, you can reparametrize any curve. So the question then is, for when we get our result for the scalar line integral, does it matter which parameterization we use? Fortunately, there's a theorem that tells us it does not. So we can always just pick whichever parameterization we want. Okay. And then just one comment, another comment here about the fact that always keep in mind that the parametric forms or equations are always more general than our classic equations without the parameter. So, for example, the integral from a to b of fx dx is actually a special case of the parametric form. So how do we get that to, how do we show that? So we just think of it as a parametric, as a curve from a comma 0 to b comma 0. And the parameterization for that is just x equals t, and then y has to be 0. So we take our general formula for our scalar line integral, the integral over the curve of f ds, and now let's rewrite it parametrically. So it's the integral as t goes from a to b, f of x comma y, times dx dt squared plus dy dt squared, square root of all that dt. But now plug in what we know. We know x is really the same as t, and y is really 0. So f of x, y just becomes f of x comma 0. T going from a to b is just x going from a to b. Dt is really just dx. And dx dt is just 1. And dy dt is just 0. So rewrite all of that, and you just get the classic integral. So this is really, scalar line integrals are really just a generalization of the integral, of the scalar line integral. In other words, integral of f dx is just is the special case for the integral of f ds. And also just a reminder, there are many equivalent notations for f. This can be confusing, but all I'll say is use whichever one you like. So you can write it as f of xy, or you can write it as f of t, or you can write it as f of r, etc., etc. You can write whichever one you like, whichever one helps you remember what is going on in the function. But it's important to remember that f is a function of x and y, which we can also write as r, the vector r, but those are really functions of t as well. Okay. So this was writing down a scalar line integral in 2 dimensions. And of course, everything we've done here, we can stretch it out to 3 dimensions. So it looks like pretty much exactly as you would imagine. So it's the integral over a curve of f of now it's x, y, z. And we still have ds, but ds is now dx dt squared plus dy dt squared plus dz dt squared, square root of all that dt. And then here's an example. So find the area under the function f equals y sine z along the curve c defined by r equals cos t sine tt for t goes from 0 to 2 pi. So how do we do this? Basic scalar line integral formula. It's the integral of f ds over the curve c. So now let's set it up. So we already have our parameterization for the curve because that's given by the formula for r. And then we just need to make the parameterization for our function, for our function f. So our function f is just y sine z. So it's going to be sine t times sine of t. So there's your function written parametrically. And then we need to convert ds. So ds is just going to be x prime squared plus y prime squared plus z prime squared, square root of all that. And then the boundaries are going to are given, and those are just 0 to 2 pi. So x prime is just negative sine t, y prime is just cos t, and then z prime is just 1. So put that all together, and you just get the square root of, well, sine squared plus cos squared is just 1, so it's just the square root of 2. So you wind up with the integral of square root of 2, and then sine squared t dt. In order to integrate sine squared, we have to use our double angle formula. So that's just right here. It's 1/2 1 minus cos 2t. That's the integral we've done before. So pulling out the constant of rad 2 and pulling out the constant 1/2, you get rad 2 over 2. And then integrating what's left, the 1 minus cos 2t, the integral of that is t minus half sine 2t. And now we just evaluate as t goes from 0 to 2 pi. So plugging in 0, we're just going to get 0. Plugging in 2 pi, and then simplifying, you get rad 2 times pi. So note that we've talked generally about this being a curve in space, and the function value represents the height, ds represents a width, so we're finding area. Function does not have to represent height. Let's see, sorry. This could, let's see. So this could represent the area under the function. However, since functions have 2 variables, you need 3 dimensions to see area. This was a function of 3 variables. So you would really need 4 dimensions to see the area, and we cannot draw that. But we understand the concept. And as I was starting to say before, the function value does not have to represent a height. So anything that was an application for the integral of f dx can also now be an application for the integral of f ds. Let's take a look at some example for that. So, one application was from density and mass. So, something we previously talked about, if we imagine that a linear object covers the line segment, x goes from A to B, and has linear density P, so that's measured in kilograms per meter, then we can find the mass by just doing the integral from A to B of P of x dx. And we can also find its moment, the integral of x times P of x dx, again, integrating from A to B. Okay, so that was the classic case. Now, let's kick it up a notch. We know that any integral of f dx can also be written as an integral of f ds. So how does that look now? So if a one-dimensional object shape is the curve C, defined by your parametric equation R equals x of t, y of t, with t going from A to B, and we know its linear density is the function P, but because it exists in 2 dimensions, P is now a function of x and y. Then its mass is just the integral over the curve of P ds, and then we can also find its moments. So now because it lives in 2 dimensions, it's got a moment in the x direction and a moment in the y direction. So the x moment is going to be the integral over the curve of x times P ds. And its y moment is going to be integral of the curve of y times P ds. And then, of course, that's the hard work. The easy work is that its center of mass is just x moment divided by the mass, comma y moment divided by the mass. So let's take a look at how this would work for a problem. Okay, so find the center of mass of the wire with this density, P equals x plus 2y, which forms a quarter circle with center 0, 0, radius 1, and it's in the first quadrant. So notice that if we just draw a picture to see what's going on here, my piece of wire is just the piece of the circle in the first quadrant. So it just looks like that. So notice that its center of mass does have to be somewhere in the plane. And now we're going to do the calculations to figure it out. So first of all, we need to make our so we know our basic formulas. We need to make our parameterizations. So first, parameterize your curve. It's a circle, center 0, 0, radius 1. So the parameterization for that is just x equals cos t, y equals sine t. And we just want the quarter circle in the first quadrant. So t goes from 0 to pi over 2. Next. Parameterize the function. We now know what x and y are. Therefore, p equals cos t plus 2 sine t. And then we'll also need the, in order to parameterize ds, we're going to need x prime, which is negative sine t, and y prime is going to be cos t. So put that all together and you get ds is going to be the square root of negative sine t squared plus cos t squared dt. All that simplifies, that's just 1, so it just simplifies to dt. So I did the simplifying beforehand. So now put that all together in our scalar line integral. So the mass is going to be the integral over the curve of P ds. And so parameterize the curve, t goes from 0 to 2 pi. Parameterize the function p. We just said it's cos t plus 2 sine t. And then converting, excuse me, rewriting ds. We actually already simplified it a little bit. We know ds just simplifies to dt. And now you can do the integral. So integrating, you get sine t minus 2 cos t. Plug in from 0 to pi over 2. And that works out to 3. And because we're finding a mass, that's 3 kilograms. And it works very similarly for finding the x moment and the y moment. The integral is slightly harder, but it's the same idea. So the integral for the x moment, just to go through it quickly, is always the integral over the curve of x times your density p times ds. So parameterize that. The bounds for the integral are going to be 0 to pi over 2. X is now cos t times your function, which was cos t plus 2 sine t. And then ds we know simplifies to dt. And then we'll have to integrate cos squared t plus 2 sine t cos t. So we can integrate cos squared t by using the double angle formula, as we always do. And then to integrate 2 sine t cos t, we can do, I did it, there's different ways to do it. I did it by just recognizing that as also a double angle formula. This is just sine of 2t. And then on each of these, you can do a u substitution, u equals 2t. Work it out and you get, and then after integrating, you get half t plus 1/4 sine 2t minus half cos 2t. And that way from 0 to 2 pi, so sorry, pi over 2, plug it in, and you get 1 plus 1/4 pi, which is approximately 1.79. And again, very similarly for the y moment, the integral of over the curve of y times p times your length ds. And the details are there if you want to take a moment to look. But the result for the y moment winds up being half plus half pi, which is approximately 2.07. So put that all together, and you get the center of mass is approximately 1.79 over 3, comma 2.07 over 3. It's about 0.6, comma 0.69.